Welcome to the Pico Quick Start video. In this video, we will review the components, assembly, and operation of your Pico solar simulator from G2V Optics. The Pico is designed to be an upgradable research platform with customizable features intended to meet the needs of different types of research and industry applications. Every shipped Pico includes the following hardware: a power supply with local power cable, a G2V branded alignment tool, a control box with the installed control software, and the LED illumination head. Variable spectrum control is an advanced software capability that enables individual channel control, variable air mass spectrum usage, and global intensity control. The One-Click Sun program is a simulation suite meant to streamline dynamic solar simulation for cyclic day-night testing with location, date, and time selection capabilities, as well as a simulation speed adjustment for accelerated testing. Two optional expansion modules are available for additional functionality: the IV module for photovoltaic solar cell performance testing, and a low-resolution external quantum efficiency, or EQE module, for solar cell characterization. The IV module includes an IV circuit board located inside the control box and the associated IV software suite, a silicon reference cell and housing with BNC connection posts, a set of BNC cables for the reference cell, and a set of 4-wire test clips to connect a test sample. The EQE module contains an EQE card located inside the control box, along with the associated EQE software suite, a reference diode for control measurements, and a set of 4-wire clips to connect to any solar cell sample. The Pico is also compatible with G2V's Python API for unparalleled control and automation of your experimental setup. The Pico can be mounted horizontally on a standard optical breadboard. In a typical configuration, 2 optical posts support the LED head and are screwed onto its backplate. Once the Pico is mounted, secure the optical posts. The next step is to remove the lens cover and to use the alignment tool to position the test sample at the correct working distance. Place the short piece on the underside of the lens tube and complete the magnetic lock by placing the longer piece on the upper side. To find the correct working distance, align the base of the triangular cutout to the edge of the lens tube. Next, align the active area of your sample to the cutout section of the alignment tool. The 2.5 cm by 2.5 cm area is formed by an imaginary square outlined by the cutout. Once the sample is placed at the working position, remove the alignment tool. G2V also offers an optional stand for vertical illumination. 2 coupling nuts are provided to support the LED head. Loosen them with an Allen key and screw them onto the backplate of the Pico LED head. Insert a bolt from the backside of the stand and screw it onto the coupling nut using an Allen key to tighten. Repeat the process with the second bolt. Now that the Pico is mounted, we will review how to align the test sample. First, remove the lens cover and place the alignment tool on the lens tube. Next, align the base of the triangle cutout to the edge of the lens tube. Raise the active area of the test sample to the edge of the alignment tool and center it in the cutout area. Once the sample is placed at the working position, remove the alignment tool. The first step in setting up the instrument is to connect its peripherals. Connect the illumination head to the control box using the off-white DB50 cable. Make sure to tighten the screws to securely lock the cable in place. Next, connect the HDMI cable from your monitor to the control box. To prevent damage to the instrument, always use an HDMI-enabled monitor and avoid using any adapter interfaces. Proceed to connect a USB mouse and keyboard. And finally, connect the power supply. If you purchased the optional IV or EQE modules, a set of 4-wire probes was provided. These probes are connected to the B and C ports on the front of the Pico. To connect them, simply match the sticker label on the cable to the corresponding port on the control box. Align the center pin with the socket, gently insert it, and rotate the connector sleeve clockwise to complete the coupling. These probes are used to connect your solar cell to the Pico. To use the G2V provided reference cell, included with the IV module, use the black B and C cables to connect the corresponding cell plugs to the control box. In the Pico GUI, a navigation bar is displayed in the top right. This bar shows every module currently installed in the system. The illumination toggle is an on-off digital shutter that allows the user to temporarily turn the lamp on or off without powering down the system. The spectrum viewer displays what spectral profile is loaded onto the system and can be used to visualize the spectral effects of changing individual LED channel outputs. Preset control buttons are provided to load spectral presets from the built-in library or to save user-defined spectrums for custom test recipes. Individual channel control slides enable single-channel intensity control. A global intensity slider is provided to adjust the output intensity of the LED head. There are multiple ways to adjust or create a custom spectrum. One way is by manually adjusting individual intensity sliders. To do this, simply select a channel of interest from the list. Then, using the slider, drag its intensity up or down. To commit a change to the simulator, click Apply. Spectrum adjustments are useful in a variety of applications, such as testing multi-junction solar cells. In this example, we are turning off every channel below 780 nanometers to isolate the response of a hypothetical subjunction. Once we have tuned the spectrum according to the experimental needs, it is best practice to save it for future use by clicking on the Save Spectrum button. This action will generate a preset text file, which can be renamed to a more descriptive label. One-click sun is a feature designed to simulate geographic, seasonal, and hourly irradiance. To start, go to the navigation bar and click on One-click sun. Next, select the date, time, and location to be simulated. Please note that time must be entered in UTC format. For your chosen location, it is possible to enter coordinate values in the fields provided or to click directly on the map. If desired, a speed multiplication factor can be added to perform accelerated cycles. Please note that a higher speed multiplier will reduce the smoothness of changes between simulated spectrums for different time periods. To begin the simulation, click the play button. To pause it without losing current progress, simply click the stop button. The EQE module enables current voltage circuit characterization measurements of solar cells or similar photoactive semiconductor materials. To operate, select a test preset from the Load Spectrum menu to record a normal IV curve, or maintain the lamp in an off state to measure dark IV curves. Once the test conditions have been set, click on IV Control. In this example, we will measure the provided G2V reference cell. First, connect the reference cell to the control box and load the AM 1.5G 1 sun spectrum. Now, click on Load G2V reference cell parameters. Click on Run Test to start the measurement. Once the test is completed, the analysis results panel will be populated with the photovoltaic performance data. To export the measured data as a text file, click on Save Test Results. The generated CSV file should be renamed to a more descriptive label. The EQE module allows for low-resolution external quantum efficiency measurements, which is useful to understand the general responsivity of a full solar cell device. To take an EQE measurement, first load the AM 1.5G 1 sun preset, and then click on the EQE tab on the top navigation bar. Scroll down to the Test Conditions section to enter your device and test parameters. After they are confirmed, click on Run Test to begin the measurement. To export the measured data as a text file, click on the Save Test Results and add a descriptive label for the file name.